Where's the recording? In the next section, I want to talk with you about ordered symbol tables. That's an extension of the API we've just covered and that binary search trees nicely implement. But it's an extension that drives home this point of having a dynamic array in the true sense, where you can insert elements in any position. That makes this really possible. And I haven't really commented on this after shouting it out initially. So we'll come back to that. In addition to the symbol table operations we've had before, so mainly put and get, plus deletions and so on, an ordered symbol table supports what we've implicitly assumed about the keys before, namely that they are totally ordered. A binary search tree always assumes that the keys are in some order so that you can decide what goes left and right. And an ordered symbol table exposes this order with extra operations to make it useful for the user of the data structure. So we have min and max to find the smallest or largest key in the symbol table. We have operations that find the closest to a key. If the key itself is stored, it will be returned. But if the key is not in the symbol table, you find the predecessor or successor. It's called floor and ceiling because if you think about the integers as your symbol table, then floor and ceiling in the usual way would work like this. So maybe it's a good mnemonic, whereas, yeah, that's the design decision from the book. So I just kept it that way. And then we have two more interesting operations, rank and select. Rank is given a key, and it finds the number of elements in the symbol table that are smaller, whose key is smaller. And select is the inverse operation. You give it a rank or an index, I, a number, and it finds you the element that is the ith smallest. So that also means, right, if you say select of rank of x, and x is in the data structure in our symbol table, you would always get the same thing back. So they're built so that this works. Rank would find how many are smaller than x, and then select would give you that element back. And rank and select may, by the name, not sound like this, but you can really use those two, specifically select, to simulate something like a truly dynamic array. Because select gives you access to the ith position. So you can use this to build an array as follows. You have some key value by which you keep things sorted, and then the value that you associate with that key is the actual thing that you store in the array. And then with select, you can access the ith position in this dynamic array, in this hypothetical array. And you can insert with the usual way by specifying a key that lies between two existing keys in a certain position, and it will just take logarithmic log n time if the tree is balanced, if the height is good. Now, there's one difference to an array. If you insert something in the middle, all the indices of elements to the right of that shift. Okay, clear, right? If I have an array and I want to insert a new element in here, all the elements to the right of it will have to make space for this new element. In a binary search tree, we don't touch all these elements. That's the whole point. We're not, like in an array, explicitly copying this. This array is just mentally in your head. It's a virtual array. But still, if you want to access by index, you have to somehow keep track that all the indices have moved if you insert something in the middle. That's why ordered symbol tables don't talk about indices. They have keys, and the keys stay the same. But the ranks are dynamic. The ranks can change all the time with insertions and deletions. I hope that may become clear a bit when you use this a bit. So for now, again, that's just the definition. That's the abstract data type. How can we implement this? Before we get to that, though, let me again check whether that has sunk in. That's a simple question testing your understanding of the definition, no tricks involved. But you may want to see the definition again. You may want to see both at the same time. Now it's of course very small. Lots of discussions. Shall we discuss together? All right, let me show your answers. We have a peak, but we also have many other answers. Most of you are right. So the only thing to remember is that rank returns the number of elements that are strictly smaller, which is another way of saying it's zero-based. The smallest element has rank 0. So if we do this here, remember we project elements down, then we get some sorted list. So we can do that here. And I'll ignore the other ones. The one we care about, 35, is here. And so there will be these 4, 11, 12, 17, and 28, which are strictly smaller. So the rank should be 4. That was the symbol table with the sorted operations. How do we implement this? I already said binary search tree do the trick. Binary search trees do the trick. But you have to add one tiny extra little bit. And this has become known as augmented binary search trees. The augmentation consists in having another field for each node, which stores the size of its subtree, the number of nodes in its subtree, including the node itself. That's why all the leaves have a 1. This guy has a 2 because it adds itself to that 1, 4, and so on. So you can double check on this slide whether I did it correctly. That's the invariant that we try to guarantee. So every node shall know how big its subtree is. I'll skip how to update that upon insertions and deletions. Again, the videos do it in detail. Let's suppose you managed to do this, and it's not too hard to do because say you insert another node here, 70. Whose subtrees have to change if you do this? Well, 70 is in this node's subtree and is in this node's subtree. Oh, it's a bigger one. And in this node's subtree, and it's in the entire tree. The roots of these trees, let me get rid of that because it's not so helpful to see, I think. The roots of these trees are this one, and this one, and this one, and this one. That's exactly the nodes on the search path. So we visited these guys anyways. So we might as well, while we do the search, increment their size by 1 because they each gain one new node in their subtree. So that's if we add this one here. Okay, now I just said I don't show you how to maintain it. No, I did. It's not that hard, that's the point. So how can we use this for our operations? Let's do an example for rank. We're trying to find the rank of 35. As always in a binary search tree, we'll start with a search because that's pretty much the only thing it can do. So that's always a safe bet. So we go all the way down here until we find that node. Now rank is supposed to return, as we've seen in the example, 4, right? We find the element here. Rank is the size of this. Now, how do we get this from the nodes that we have on the search path without visiting all those nodes? We don't want to pay extra. So what we'll do is we'll split the contribution of nodes that are smaller into several parts. One contribution is visited nodes that are smaller. These are the ones where we took a right turn. So it's the 12 and the 28. Right? Whereas whenever we took a left turn in the path, we know that that node was too big, and actually also its right subtree was too big. We have to add another contribution. Whenever we do a right turn, like in this case, we follow a right pointer, we have skipped an entire subtree, namely this one, and here we do it again. These we don't explicitly touch, but we can check how big they are by peeking into that node's size field. Okay, so in this case, this both works out to 2. But in general, these pink subtrees could have been arbitrarily big. All I need to do is visit this child and look at how big its subtree is. That's the whole magic why the subtree sizes are useful. You can visit the node and do one check, and then you know how big the subtree is without further looking. And that's rank. So to put that into code, you would have to do the search, keep a count whenever you find a node that's smaller, whose key is smaller. And if you found such a node, you can add its left subtree. How do we do the other operation, the select operation, which is the opposite? Let's do the same example. So if you say select 4, I'd like to get this one as a result because, again, remember, this is virtual, right? This array at the bottom doesn't exist in the computer memory. All that exists is the tree. I should have stressed that maybe. This is just for us to make it easier to visualize and to think about it. All the computer has is the tree structure on top. But if I have this help, I know immediately select 4 should return the 35. But how does the computer do it only knowing the tree? Well, we do a kind of search again. We start at the root. Now, we can't really make use of the key. All we can use is the subtree sizes this time. Now, the root has 16 in its subtree. That doesn't help us, but we can peek in its left. Let me show that maybe as a dotted line. So we peek into the left subtree and get out how big it is. And based on that number, we make a decision. Now, 9 is greater than 4, greater equal. which means there's enough nodes in the left subtree to contain the one that we're looking at. In another way, it means there's too many to the left of this dividing line for our node that we're looking for to be on the right side. It has to be left. The only other option would have been, I guess I should add a +1 here, or -1 on that side, because we're 0 based. If we're looking for 70 for select 9, let's do this as a second case. Select 9. In this case, I would also peek into the left. I would find rank 9, which means there's exactly 9 things in the left subtree. That means the root has rank 9. Then I can stop. Okay. So let's write this as strictly greater. In that case, we have to go into the left subtree. So we now actually follow the search path to here. Now we're in the same situation. We peek into the left subtree and look at its subtree size. That's 1. That's too small. That's less than 4. So in this case, we have to go right. But we're skipping a subtree now. By moving right, we move into this subtree. So the remaining tree that we're looking at is only this. And there's 2 to the left of that one. So that subtree only corresponds to this range. Okay, maybe I should draw it a little more carefully. So it's only covering that part. There's 2 keys that we are skipping by going left, and we have to adjust the rank that we're looking for accordingly. So when we go down this road, we change our query to select 2. We subtract 1 for the node that we just skipped, and we subtract 1 for the subtree size that we skipped. These are the exact same 2 values that we had before. I called this the green and this the purple one before. So we skip this and we skip this. Then within this tree, we do the same procedure. We're trying to select the node of rank 2. Where here we peek into the thing. 4 is bigger than 2, so we go to the left subtree. If you go left, you don't have to adjust the rank. That's the easy case. We're still looking for rank 2. We peek into the left. 1 is too small. So again, we take a turn right. But we have to select 0 now, because again, we omit these 2. The entire subtree and this node are removed from the consideration. And now we're down to this small part. And now if you say select 0, here there's nothing on the left subtree, so the root has rank 0 in this subtree. So we return 35, and that's what we wanted. Okay, so select from all the operations is the one that's most intricate, because you have to combine all the things that we've done before. But once you're over that hurdle, you have this fully dynamic array where you can insert things in any point and you can jump to any position, all bounded by the height of the binary search tree. In this case, I told you the solution without motivating why that's the solution first. And I want to finish off by telling you why that is the solution. The solution being augmenting the tree with subtree sizes. It looks like this made select rather tricky, so maybe there should be an easier way to do it. So for example, you could, instead of augmenting the tree with subtree sizes, store the rank of every node in each node. That would be super handy, because then rank is trivial. You just find the node and return the stored rank. And select would also be easy. You just do a binary search based on those stored ranks. If someone wants to shout out why that's a bad idea, you could do. This would work fine for the static problem, but not if you want to insert and delete things. So you can't really maintain this efficiently. And it's, if you draw a small example, it's obvious to see why. So suppose on the right-hand side, here's a really big subtree. And now suppose I insert a new node here. What does that do to all the ranks to the right of this red node? Well, they all have to go up by 1. I have to increase their rank by 1. If I explicitly store the ranks in nodes, I have to touch all those nodes. I have to explicitly visit them and update their rank. And I just don't have the time to do that if I want to be fast. This could be essentially the entire tree. And so we're back to linear time. Whereas subtree sizes have this lovely property that they're local. Only on the search path does the subtree size change, right? So subtree size is only changing here +1, here +1, and here +1. And I don't have to visit all of those guys. It's just one path.